In this video, we talk about direct product groups. The idea is to take several groups and put them together to form a new group. To begin, let's have a look at an example. So you're looking at a group table, and before we start doing a lot of talking about it, I'd like you to consider two questions. The first is, can you determine how this operation is working? And the second is this group cyclic? Now would be a good time to pause the video and think about those questions. Now, I'm assuming that you have paused the video and thought about those questions for a little while. So regarding the first question, let's take a look at a couple of elements in the group. Let's suppose we look at 1, 1 and 2, 1, for instance, and we want to combine them together using the operation. So if I take 1, 1 and 2, 1, you might have noticed that you combine elements in this group by first looking at combining the first coordinates or the first elements, so the 1 and the 2 maybe go together. And then we combine the second coordinates. Now we have to know in what setting we're adding these things. So the 1 plus 2, that's going to happen inside of Z3. And the 1 plus 1 is going to happen inside of Z2. And notice that 1 plus 2 is equal to 0 in Z3. 1 plus 1 is equal to 0 in Z2. And if we remove the comma, that just gives us 0, 0, which is our result. Okay, so this group, the set here that we're considering for this group, can be thought of as the Cartesian product set Z3 cross Z2. And we can put an operation on it just by adding in Z3 in the first component and adding in Z2 in the second component. All right, now on to the second question, and that is whether this group is cyclic. Well, maybe you determined that the answer is yes. And in fact, if we look at our element 1, 1 again, and we start taking, applying 1, 1 to itself over and over again, let's see what happens. So if we take 1, 1 together with 1, 1, we get 2, 0. And then if we take 2, 0 together with 1, 1, we get 0, 1. 0, 1 together with 1, 1 is 1, 0. 1, 0 with 1, 1 is 2, 1. And then finally, as we saw, 2, 1 together with 1, 1 is 0, 0. So if I just take repeated sort of multiples or powers of, of 1, 1, then I actually get the entire group. So we would write that G is generated by the element 1, 1. The example on the previous slide can be generalized. If we take a list of groups, say G1 through Gn, we can form their Cartesian product G, and that new object, this Cartesian product, is itself a group under a natural operation, this star, where when you take two n tuples and multiply them together, you just multiply them component-wise. So the new n tuple is G1 H1 through Gn Hn, where each one of these products is computed in the appropriate group. that means, for instance, that little g1 times little h1, that product needs to be computed inside of the group capital G sub 1, and so on and so forth until we get to the end of the n tuple, where that last product needs to be computed within the group capital G sub n. So a group like this capital G, it has a name. It's called the direct product of the original groups, G sub 1 through G sub n. You know, a few questions for you to think about. Maybe you'll want to pause the video and think about them. What is the identity in a group like this? And what sorts of things can we tell about capital G just by knowing a few things about the component groups, G1 through Gn? For instance, if all of the G sub i's are abelian, will capital G be abelian? If all of the G sub i's are cyclic, will capital G be cyclic? Okay, take it now that you've paused the video and thought a little bit about these questions. So for identity, the identity in capital G, well, since the operation is a component-wise operation, we would expect the identity to be just the tuple that we form from the identities that we get from each one of these individual groups. So the identity in G1 would be the first component of the identity, and then the identity from G2, and so on and so forth. Okay, now what about this business about being abelian? Well, it turns out that if all of the little G sub i's, if all of the groups G sub I are abelian, then the direct product will also be abelian. And we can see this just by, you know, if we take G sub 1, G sub n, and we apply it to H1 times Hn, we know from our definition above that this is G1 H1 through Gn Hn. But each of these groups G sub I is abelian, so in each component we can reverse the order of the product. And then we undo the operation, and this is H1 through Hn times G1 through Gn. And so apparently the order in which we multiply these things does not matter, so the group is abelian. Okay, finally, the question about whether the capital G sub i's being cyclic implies the direct product is cyclic. Well, that's a little bit harder question that we'll talk about on the next slide. So it turns out that direct products of cyclic groups do not need to be cyclic. And we don't really need to go very far to find an example of a direct product of cyclic groups that fails to be cyclic. So for instance, if we look at Z2 cross Z2, well, Z2 is a cyclic group. It's generated by 1, but this direct product fails to be cyclic. And you can see that by noticing that every element in this group has order 2, right? So this 0, 0 is our identity. And notice that the square of every single element in this group is the identity. And so that means that there's no element of order 4, meaning that there's no sort of cyclic generator of this group. So after that last example, we could just brush our hands off and walk away. But we do want to know when a direct product group is cyclic. And in order to answer that question, we're going to need to know how to compute orders of elements in direct product groups. And hence we have this example. So we're going to start with this element 966 inside this direct product group, Z18 cross Z9 cross Z8. And we're going to compute its order. So we start with 1966, which is just itself. Then what do we want to do? Well, we want to apply 966 to itself. And since this is an additive group, we're going to be looking at multiples instead of powers. So I take 966 and I add it to itself. And I see that 9 plus 9 is 18, which is 0 inside of Z18. 6 plus 6 is 12, which is 3 inside of Z9. And 6 plus 6 is 12, but that's 4 inside of Z8. So now we keep going. And you might be wondering, well, what are we shooting for? Well, remember that the identity in this group is 0, 0, 0. And so I'm looking for the first multiple that gives us 0, 0, 0. So 3 times 966. So that means that we take 0, 3, 4, and we add 966. 6 and 3 is 9, which is 0 inside of Z9. 6 and 4 is 10, which is 2 inside of Z8. So we keep going like this, and you might be wondering, well, when is this ever going to stop? Will it stop here? Well, 9 and 9 is 18, which is 0. 0 and 6 is 6, which is just 6 in Z9, so apparently it won't stop here. 6 and 2 is 8, which is indeed 0. So we got 2 zeros, but we didn't get 3, which is what we needed. And now you can keep going like this, in this fashion, and the very first time that you'll obtain the identity is with the multiple 12. So once you finally arrive there, then you'll be able to conclude that the order of this element, 966, is equal to 12. Now, it would be really nice if we knew some way to compute this order without having to just simply compute all the powers or multiples of the given element. And if you think about it, there should be some way, to make this computation easier. So one thing you might notice is that this order, this 12, should be dependent somehow on the order of these individual components, 9, 6, and 6, within their individual groups, right? Z18, Z9, and Z8. And in order to make all of these components roll around to zeros, like we did here, you would expect that the order, this number 12, should be some kind of multiple of the order of the component elements. And in fact, that's really what's happening. Notice that the order of 9 inside Z18 is 2. The order of 6 inside of Z9 is 3. So that's inside of Z9. This is inside of Z18. And the order of 6 inside of Z8 is 4. And lo and behold, this number 12 is a common multiple of them. And in fact, you would expect it to be, if it's going to be the smallest possible multiple, then we want it to be the least common multiple of 2, 3, and 4. the example on the previous slide leads us to a theorem. So we let capital G be a direct product group. The first part of this theorem tells us how to compute the order of an element in capital G. So if we have a little g and we want to compute its order, apparently all we need to do is take the least common multiple of the orders of its components, little g1 through little g sub n. That, of course, really only makes sense when each of the components has finite order. Now, the second part of the theorem sort of gives us an answer about when, capital G is a cyclic group. So if each of the component groups is a finite cyclic group, then the direct product group will be cyclic if and only if the orders of the component groups are pairwise relatively prime. Now, proving this theorem, we first start with part 1 of the theorem, and we want to know, well, what happens when we take g to the m and get the identity? So we're looking, remember, for the minimal positive m so that g to the m is the identity. So anyway, if you have g to the m equaling the identity, we know from the definition of the product in the direct product group that means that g sub 1 to the m up through g sub n to the m, that they all must be individually equal to the identity in their respective groups. And then you will remember from section 4 that means that the order of each little component element must divide m. Now, another way to say that is that m is a multiple of each of those orders. Now, remember, we're seeking the order of little g, and that means that we want this m now to be as small as possible. So we're looking for the smallest multiple of all of the individual orders, right? So that means that this minimal m should be the least common multiple of all of these. And that proves part 1 of the theorem. Now for part 2, we start off by assuming that each of the component groups is cyclic and is generated by some little g sub I. And now we want to show that the direct product group is cyclic, which means that we need a generator for that direct product group. And probably the only reasonable candidate would be this element little g that we get by taking all of these individual generators of the component groups together to form little g. Okay, so now we know, that let's assume now that these, orders of the component groups are pairwise relatively prime. Well, since each of those are cyclic groups, that means that the orders of the generators are relatively prime, which means that if I now take the order of this little g and apply part 1 of the theorem, I'm supposed to take the least common multiple of all of these individual orders. But remember, all of the individual orders are relatively prime, and that means that the least common multiple is just the product of all of them together. Now, the order of each one of these guys is exactly equal to the size of its component group, because each little g sub I generates, the component group capital G sub I. But now this product here, that's the size of the Cartesian product that gives rise to G. So what have we done? Well, we've shown that the order of this little g is equal to the order of the group. And that means that the powers of little g must exhaust every element in capital G. And that implies that G is cyclic. Now, this theorem, this argument can be reversed to give the if and only if portion. Okay, let's apply this theorem to answer a couple of questions about our favorite direct product group, Z18 cross Z9 cross Z8. So one of the questions is that group cyclic? And from part 2 of the previous theorem, we see that each one of the component groups is a cyclic group. And so that means in a finite cyclic group. And that means in order for this direct product to be cyclic, the orders of each of these component groups must be pairwise relatively prime. And we see that that is not the case here, because 18 is the order of Z18. And, 9 is the order of Z9. And 18 and 9 are not relatively prime, right? They both have 9 as a common divisor. So the answer to that second question is no. That's by part 2 of the theorem. And that leaves us to the first part of the question, where we're supposed to compute the order of this element, right? Now, we could go back to what we were doing a few slides ago and just successively take multiples of 4, 6, 6, and then just see and wait until we wind up with, the identity. But we learned from the last slide that, that the order of this element is going to be the least common multiple of the order of 4, the order of 6, and the order of 6. So now remember, we got to remember where we're working. So in the first component, we're in Z18. In the second component, we're in Z9. And in the third component, we're in Z6. Back in section 4, we learned how to take orders of elements in these modular integer groups. So in particular, if I want the order of 4 in Z18, I take 18 and I divide it by the greatest common divisor of 4 and 18. And then for the second one, I take 9 divided by the greatest common divisor of 6 and 9. And finally, for the third, I take 8 divided by the greatest common divisor of 6 and 8. That turns out to be the least common multiple of, we get 18 over 2, 9 over 3, and 8 over 2, which is the least common multiple of 9, 3, and 4, which I believe is 36. So that's a lot easier and simpler than taking the element 4, 6, 6 and repeatedly applying it to itself until we get the identity.